Hello everyone and welcome to chapter number 4 in the three-phase induction machine course, motor parameters determination. For those who didn't follow us from the beginning, in chapter 0 we covered the revision material or the material we need for this course. In chapter number 1 we covered the rotating field theory. Chapter number 2 we covered the construction, theory of operation and equivalent circuit. In chapter number 3 we covered the power and torque calculation. So in this chapter, we're going to look for how to determine the motor parameters. So what are the contents of this chapter? In this chapter, we are going to introduce the motor parameters and how to calculate these motor parameters using Turner's ratio test, DC test, no-load test, blocked rotor test, and we are going to have examples and we are going to wrap up this chapter by a summary. So once we finish this chapter, we are going to understand how to determine the motor parameters of squirrel cage and slip ring induction motor using analytical methods, and then we are going to apply the same techniques in the lab to find these motor parameters. So we are going to start this chapter by video number 1. In this video, we are going to cover motor parameters, Turner's ratio test, and DC test. Let's start by asking ourselves a question: what are the motor parameters? So to answer this question, we need to recall the equivalent circuit. This is the first approximate equivalent circuit. As we can see here, it consists of lump elements like resistance and inductance. The voltage and currents are rated values, while the resistance and reactance here are the motor parameters. So motor parameters are R stator, X leakage stator, R rotor at standstill, X rotor, leakage rotor definitely, core resistance and magnetizing reactance. So the question, why we want to know these parameters? In the previous chapter, these values are given. So why I want to determine these values? So these values or these parameters play an important role in the operation and management of the motor. For example, design analysis, performance evaluation, regular maintenance, speed and position control, the replacement of faulty components as well. So if you determine these values or these parameters, so you can optimize your motor performance, ensure reliability, and diagnose any issues with your motor. So what are the tests you can use to determine these values or these parameters? So we have Turner's ratio test to determine the Turner's ratio between a stator and rotor winding, DC test to determine the stator resistance, and we can use this test as well to determine the rotor resistance for a slip ring induction motor. No-load test is used to determine R core and XM, and blocked rotor test is used to determine R rotor, X stator, and X rotor leakage values. So let's start these tests. Turner's ratio test. So in this test, we are going to determine the Turner's ratio or the effective Turner's ratio between the stator and rotor winding. For a machine like slip ring induction motor, we have three-phase winding in the stator and three-phase winding in the rotor. So the stator has impedance R stator and X stator, and the rotor has R rotor and X rotor. So we want to make a referring from the rotor to the stator side to solve the approximate or exact equivalent circuit. So we need to know what is the Turner's ratio. This machine is accessible from the rotor side, so we can know what is the value for the Turner's ratio or what is the effective Turner's ratio. We cannot access the rotor of the squirrel cage, so the squirrel cage is another analysis, complex analysis, but for the squirrel cage we can calculate the rotor impedance referred to the stator side from the stator test. For this machine, we need to know sometimes the effective values or the values of the rotor impedance in the rotor, because this machine could be used as induction generator for wind turbine applications, as an example. So for this test, what we are going to do, we are going to connect the machine as we are going to see here, that we have the machine terminal box. So the stator could be a star connection. We are going to apply AC source between any of the two phases, A and B for example, but we are not going to short circuit the rotor to prevent this machine from creeping or rotating. So we need to make the stator frequency equals the rotor frequency. So if the machine is at standstill, F stator will be the same like F rotor. So we are going to measure the voltage in the stator side and measure the voltage in the rotor side. And because the number of turns per phase in the stator is not equal to the number of turns per phase in the rotor, so E stator per phase over E rotor per phase equals T phase stator multiplied by the winding factor of the stator over T phase rotor multiplied by the winding factor of the rotor. You didn't tell us anything about the winding factor. That one is another story. That one is a separate video. So we assume that we know the winding factor of the stator and winding factor of the rotor. So the turns ratio will be the ratio between phase voltage in the stator to phase voltage in the rotor. So that one will be the machine in this case. So we are going to apply this test, but if you notice here, I apply that one between two lines, so you need to convert that one to phase value, and that one will be internally connected to the star, so you are going to convert that one as a phase value. So we are going to find E stator phase to E rotor phase. I know that one will be over root 3 and that one will be over root 3, so root 3 will be cancelled from the numerator and denominator, but the equation is phase value to phase value. Once we calculated that one, or we measured that one in this side and we measured that one in this side, we will know what is the turns ratio. If we have exact value for our rotor in the rotor side, so we can make a referring for the stator side, that one will be R rotor dash. So R rotor dash will be R rotor multiplied by the turns ratio square. So that one will be the referring, and the same for X rotor. And when we are going to solve the exact or approximate equivalent circuit, as usually we use the values referred to the stator, we are going to cancel this dash as the default the R referred. The second test is DC test. Why we need this test and how we are going to do this test. So the DC test is used to determine the stator resistance. Please remember that stator resistance is a small value. So we are going to apply a small DC voltage. DC voltage. So this is AC machine. Yes, we are going to apply a small DC voltage and small voltage to protect this machine from high current. Then we are going to increase this voltage gradually until we reach a value of a current close to the rated value. So we are going to record these values for the voltage and current, and then we are going to calculate this DC resistance. How we are going to do it? So in the lab, we are going to connect the machine terminals, two lines, to a DC supply, as we can see here. And definitely the machine is not going to rotate because we apply DC source. So the value for this resistance, DC resistance, still not the stator resistance, that one is called DC resistance, is VDC over IDC. We are going to plot a curve like this one and take the difference delta V over delta I and determine the value as a DC value. So if we have this resistance at DC value, so how we are going to calculate the stator resistance? That one based on the machine connection, star or delta. Let's start by star connection. So in the star connection, we're going to connect the DC supply, V supply, across two of the phases, for example, A and B, while phase C is not connected to anything. So the current is out from the source going through phase A, and phase A is in series with phase B, so return back to the supply as we can see here. So we are going to measure VDC and IDC. As you notice here, I put two equals, so this means DC measurements. So RDC over 2 represent the resistance R per phase. But that one is still not AC resistance. That one is still DC because we are going to apply DC supply here across these two phases. So how to convert this R to AC value? So you know that from the circuit fundamentals that if we have a DC source applied to a wire, the current is going to scan all the cross-section area. While if you apply AC source, the current is going to the surface due to a factor is called skin effect. So we are going to consider this skin effect for 50 Hz or 60 Hz. We are going to say that R stator per phase equals 1.11 this value of R. R equals here in star connection RDC over 2. Definitely this factor depends on a lot of stuff, something like the frequency, the cross-section area, or the material type, copper or aluminium. But here we are going to consider that one in the common cases that 50 or 60 Hz, that R stator per phase equals 1.11 R. What about the delta connection? In the delta connection, we are going to connect the DC source between two of the phases A and B, while phase C is not connected to anything. So like the star connection, the current is going out from the source. We'll be measuring the voltage here, VDC, and the current IDC, and going through this delta connection and return back to the source. But at this point, the current will be distributed between R and this R, and due to phase C is not connected to anything, so the current here going through this R and this R and the R in series. So we have two resistances in series, two R, the R in parallel with one resistance, which is R. So in this case, we have the equivalent resistance measured by this source, that 2R is parallel with R, so that one will be 3R. So cancel this one. We have the equivalent resistance 2 over 3R, and that one is the measured resistance from the source. So what is the value of the resistance R based on VDC IDC? So in this case, R per phase is 3 over 2 RDC. Still, that one is a DC resistance. We want to calculate that one, or to find this one as AC value when we are going to apply AC source. So in this case, we are going to apply the skin effect. So R stator equals 1.11 R. So look here again, these two resistors are in series in parallel with this one. So that one is the equivalent resistance for this part. And we measured here RDC. So R from RDC equals 3 over 2 RDC. Can we do this test without using a DC voltage source? Yes, we can use the normal multimeter or ohmmeter, but that one depends on the machine connection. If we have a star connection, we are going to connect this multimeter, as we can see here, between phases A and B, and we have two resistances R and R. So this R we are searching for equals the measured value RDC over 2. Someone said that's why I do that one. I'm going to connect directly the ohmmeter between A1 and A2. I'm measuring the resistance R, where R in this case equals RDC. 100% correct. But for delta connection, we're going to connect the machine as we know, start to finish, or finish to start. It depends how we are going to connect your delta as we learned it before. But that one is connected between A2 and B2 here. So the resistance we are searching for is 3 over 2 RDC measured by this ohmmeter. But please note, all of these resistance are DC values, so we need to consider the skin effect, where the stator resistance per phase is 1.11 RU measured either star connection or delta connection. For star connection, you measure between two lines, or you measure across one phase. We are going to do that one practically now and check that one for the motors we explained or we used in chapter number 2. What we see here is one of the stators I used before in chapter number 2 to explain the machine construction and the three-phase winding. What we see here, we have the terminal box. We have 6 terminals, 1, 2, 3, 4, 5, 6. I connected these 3 points together to make a star point, as we can see here. So I'm going to use the multimeter here to measure the resistance. So I adjusted that one for 200 ohm. If we need to change the scale, we can change it, but I presume that the stator resistance is a small value. So I'm going to measure the resistance between phases A and B now. So that one will be A and B measurements, something like 35.9. Between A and C, we have 35.5. Between B and C will be something like 35.9. So let me take the value something in between. So R DC equals 35.8 ohm. So the resistance R, because the R2 resistance are connected in series, so we are going to divide that one by 2, so RDC over 2, so that one will be 35.8 over 2, so that one gives us 17.9 ohm per phase. So that one is R, but that one is not the stator resistance. The stator resistance will be 1.11 multiplied by 17.9, which is the skin effect. So the answer is something like 19.87 ohm per phase. So we can measure this resistance by another way. Rather than to measure between two phases, we are going to measure between one of the phases and the return, or the start point. So the resistance is something like 17.8 ohm. So the resistance will be R 17.8 ohm, that one per phase. So that one will be R stator 17.8 multiplied by 1.11, so that one gives us something like 19.75, and we can say that 19.8 ohm per phase. We can remove the star point and we measure for the go and return for any of the phases. So that one is phase A and that one is the return of phase A. So that one gives us something like 17.8 as well. So give the same answer, which is 19.8 ohm per phase. So our stator will be 19.8 ohm per phase for this machine. Let's have another machine. The previous machine was star connected, or we measured between the phase and the neutral point or the return of the phase. So here we have delta connection. We have 6 terminals, 1, 2, 3, 4, 5, 6. We connected start by finish, start by finish, start by finish. So we can measure between two of the points here. So if we measure between phase A and phase B, so let's open that one first. Resistance 200 ohm. So we are going to measure between this point and this point. So the measurement is 30.6. If we measure between A and C, so that one will be 30.8. Between B and C, something like 30.8 as well. So we can say that if we take R DC equals 30.8, so R we are searching for will be 3 over 2 multiplied by 30.8. Let's use our calculator here. So that one will be 3 over 2, 1.5 multiplied by 30.8. So that one gives us something like 46.2 ohm per phase. So R will be 46.2 ohm per phase. So we need to use a skin effect to calculate R stator. 1.11 multiplied by 46.2. So multiply this value by 1.11. So the answer is 51.3 ohm per phase. So R stator for this machine, 51.3 ohm per phase. So it's high value, yes, but this machine is a small machine in the power rating and lower current values. So expected that to have the resistance higher value. Returning back to our slides to recap this video. So in this video, we answered the question, what are the motor parameters? They are stator resistance, rotor resistance at standstill, stator and rotor leakage reactance, core resistance, and magnetizing reactance. Then we start to perform the tests one by one. So the first test was Turner's ratio test, and that one is the effective Turner's ratio between the stator and rotor winding, and that one is mainly for slip ring induction motor. Squirrel cage, we cannot access the rotor side. So we are going to apply small AC voltage from the stator side. We are going to measure the voltage from the rotor side. So in this case, we are going to have the Turner's ratio E stator phase over E rotor phase. If the machine is a star in the stator and definitely is internally connected as a star in the rotor, so that one will be E stator phase over E rotor phase. But if the machine is delta in the stator, so that one will be a phase voltage, so we need to modify the voltage in the rotor by dividing this value by √3. Moving to another test. DC test is used to determine the stator resistance per phase. How we are going to find the stator resistance? Either we are going to apply a DC voltage to the stator side, and then we are going to measure different values from the voltage and current, and then take the average of these values. So VDC over IDC, we're going to have RDC. So in this case, we are going to look for the machine connection, star or delta. If it's star, the R or the resistance per phase will be RDC over 2, and then we need to modify this value by the skin effect. If the machine is delta connection, so RDC will be 1.5 or 3 over 2 VDC over IDC or 3 over 2 RDC. Then we are going to modify this value by the skin effect. We are going to take the skin effect 1.11 for 50 and 60 Hertz. If we're going to work with different applications like aerospace applications, 400 Hertz, we might modify this value or this skin effect. Also, we can use a quick method to calculate the DC resistance or to measure the DC resistance using the multimeter. So the question now, which one is better? I'm not saying one is better than the other, but the multimeter is a quick method to calculate the stator resistance or to know the stator resistance. But the method using the DC supply can be used for high power rating machines for more accuracy, because sometimes you're going to find that the stator resistance will be fraction of ohms, so you need more accurate results. But a quick result you can measure that one using the multimeter. Also, that one can be used for low power machines, something within the 5 horsepower. So to have the resistance of the stator something like from 1 ohm up to 50 ohms, as we saw in this video. What will I watch in video number 2? In video number 2, we are going to have no-load test and blocked rotor test to determine the other parameters. See you in the next video.